Let's practice a few of these net ionic equations. The first step is to rewrite this equation so it looks like what's actually happening when this is in water. Because this HCl is aqueous, we know what we are seeing here is H plus, and I'm going to leave off the states until we get to the end, and then I'll add them back on. And Cl minus. And because the zinc sulfide is also aqueous, we have Zn plus 2 because the sulfur is minus 2. Making, now this is not aqueous, so we're not going to break it apart. We're going to leave it as H2S, and I'm going to say gas, so I remember why I didn't break it up. But this final is also aqueous, and the zinc is still plus 2. So now let's look at this. And we're going to find what we call spectator ions, the things that do not change. So we have chlorine and chlorine, and both of those are aqueous. If I left the symbol off, it usually just means aqueous. So we can mark those out. The H plus, there's not an H plus on the right, but there is a zinc on both sides. So when we cross out the spectator ions, we get that our net ionic equation is H plus aqueous plus the sulfide ion, also aqueous, making H2S, which is a gas. Okay, so this is what the net ionic equation tells us what's really happening. All these ions are in place in the water, and these two ions are coming together to make this gas. That's the only real difference that's happening. Those other things are staying in aqueous solution. We do still need to balance this, but this should be pretty easy. We just need 2 hydrogen ions. Let's try another one. So for this example, we have a single replacement reaction, which we do see occasionally. When we break this out into the ions, we do not break up this chlorine because it's a gas, but the sodium bromide does get broken out. And then on the product side, the liquid bromine stays together, and the sodium chloride breaks up. So next we find our spectator ions. And if we look, chlorine changes, sodium does not change, but the bromine changes. So for this one, our net ionic equation Cl2 in a gas plus bromide in an aqueous solution create liquid bromine and aqueous chloride ions. And if we balance this, we put a 2 here and a 2 here. And now this kind of equation we haven't talked about yet, but we're going to talk about soon, because you can see it's still chlorine and bromine separate, and then chlorine and bromine separate relatively. What's happening here is that electrons are being transferred, and this is called a redox reaction, or an oxidation reduction reaction. We'll learn a lot more about that in the next few pages, but here's a little preview. Let's try these next 2 examples. So for this first one, we're looking at it, and you might wonder, do you have to break the polyatomic ion up? Is this chlorate? You do not. You can just keep it as itself. And it's got a charge of -1, which means that our lead is +2, because there's 2 of those. And our sodium iodide also breaks up. And you can see this does not separate out. And you know you will always have something that's not aqueous as a product. We've talked about double replacement reactions and if they occur or not. They're not going to occur if you don't make something new. If they were both aqueous, then we would cross out everything as a spectator ion. When we look through for our spectator ions, you can see our lead changes, but our chlorate does not. And our sodium does not change. So this will give you the aqueous ion here, plus this aqueous ion, coming together to make a solid. We need to balance this. There you go. So hopefully these are fairly straightforward. You're just breaking it down into the smallest components and then basically cleaning it up a little bit. Let's do one more. Let's do another single replacement. You should hopefully get to the point where you can look at the type of reaction it is and kind of predict what it's going to look like. So the zinc does not break out into an ion because it's a solid. The hydrochloric acid does because it's aqueous. And this zinc is +2 because it's a gas. We don't break it apart. We look for our spectator ions. The zinc changes, but the hydrogen changes, but the chlorine does not. So this is going to look just like the second one. And the only thing that's really happening here is that electrons are changing place because the zinc goes from being neutral to having a +2 charge, which means that it must be losing electrons. And the hydrogen goes from positive to neutral, which means it must be gaining those electrons. And you can see the number of electrons even balances out because matter is conserved. The zinc goes from 0 to +2, which means it loses 2 electrons. And then we have 2 hydrogen ions right here that are going from +1 to 0, which means each is gaining 1, so gaining 2 total electrons. And this is a great introduction to redox reactions. Please note that there are a lot more practice problems of these in your book. They also help you practice predicting products. So if you need more practice with this, please see the note below about where to find it in your book and where to find those answers. Let me know if you have any questions.